My voice is clear? Am I audible?
Yes, sir.
Okay. Yes. What we have discussed in previous lecture? Okay, we have seen the some basics of the synchronous motor. What is synchronous motor? What is difference between the induction motor and synchronous motor? Okay. What is difference between the DC motor and synchronous motor in the case of construction? Clear? And also we have seen some components of the synchronous motor. Okay, what are the parts of synchronous motor? Stator, rotor. Okay. Next, what is stator? What is rotor? Everybody knows. Frame. What is the function of frame? What is the function of exciter? So all these things we have seen, and also we have discussed the types of the synchronous motor. Also, we have discussed types of synchronous motor. What are the types of synchronous motor? Based on the excitation, the synchronous motor have been classified in two types. Based on the excitation, the synchronous motor has been classified into two types: non-excitation synchronous motor and excited synchronous motor. And what is excited is synchronous motor? What is the non-excited is synchronous motor? Generally here, the excitation is nothing but, in the case of induction motor, already I told yesterday, in the case of induction motor, we are going to give a supply to the only stator winding, but we are not giving any supply to the rotor winding. Clear? So, but in the case of DC motor, we are giving the supply to the both windings, armature winding as well as field winding. Armature winding as well as field winding. So, but in the case of DC motor, we are giving the DC supply both windings. Stator and rotor are armature and field. But here synchronous motor, small difference is there. We are going to give the AC supply to the stator winding, and we are going to give the DC supply to the field, armature winding. That is the rotor circuit. DC supply to the rotor circuit. Clear? So if winding is present in the rotor circuit, so definitely we have to give the DC supply for that rotor circuit. If winding is not present, so no need to give the supply. So how the rotor can rotate? Based on the magnets. Okay, if any permanent magnets are placed in the rotor circuit, okay, no need to give any supply. So that type of motors can be called as a non-excited non-excited synchronous motor, because we are not exciting any rotor circuit. We are not exciting any rotor circuit. Okay, we are not giving any supply to the rotor circuit. So obviously the rotor circuit will not be excited. That's why the type of motors can be called as a non-excited synchronous motor. So excited synchronous motor is nothing but the motors which are having the winding in the rotor circuit, the motors which are having the winding in the rotor circuit, and this rotor circuit will be excited by the DC supply, and this rotor circuit is excited by the DC supply. So this type of motors can be called as a synchronous direct current excited synchronous motor. Okay, non-excited synchronous motor and excited synchronous motor. Again, this non-excited synchronous motor have been classified into three types: hysteresis synchronous motor, reluctance synchronous motor, permanent magnet reluctance motor. Okay, sorry, permanent magnet synchronous motor. So all these things we have discussed yesterday. So what is speed? Just generally, the speed range of synchronous motor from 150 to 150 rpm to 1800 rpm. The speed is synchronous, does not depend on the load. Okay, conditions. Speed always remains constant from no load to full load. So this part, what we can see here, in the case of induction motor, okay, the rotor is always rotates less than the synchronous speed. The rotor is always less than the synchronous speed. So the rotor speed is never equal to the synchronous speed in the case of induction motor. At the same time, if any load is applied on the induction motor, at the same time, if any load is applied on the synchronous motor, if any load is applied in the induction motor, the motor speed is going to decrease. The motor speed is going to be decreased. But in the case of synchronous motor, the motor speed, that is rotor speed, is synchronized with the rotating magnetic field, that is synchronous speed. Okay, the motor speed or rotor speed is synchronized with the rotating magnetic field. Okay, and this motor will rotates at constant speed is equal to the synchronous speed, irrespective of the any load. Irrespective of the any load, even the load is applied, the speed is same as the synchronous speed. Even the load is not applied on the motor, the speed is same as the synchronous speed. Clear? So that's why the motor speed is always remains constant from no load to full load. The motor speed remains constant from no load to full load. But in the case of induction motor, the load is varies, depends upon the load. If the load is applied, the motor speed is decreases. Okay, the load is decreases, the motor speed is increases. That is depends upon the load. Okay, but here irrespective of the load. Starting torque. External force is required to start the synchronous motor as it has no starting torque. So obviously, synchronous motor is required some external supply. Okay, it is having it doesn't have any starting torque. For providing the starting torque, we need an external supply. Okay, rating of the motor. So it is available from 150 kilowatt to 15 megawatt. Okay, the synchronous motor can be available from 150 kilowatt to 15 megawatt. Efficiency of the synchronous motor are highly efficient machines. Their efficiency is much greater than induction motor. So simply what we can say, the induction motor, the efficiency of the synchronous motor is somewhat higher than the induction motor. Maintenance. The synchronous motor uses brushless exciter, which decreases the maintenance problem. The synchronous motor uses the brushless exciter, which decreases the maintenance problem. So here, in the case of DC motor, we are using the commutator and brushes. So, but here we are not using any commutator and brushes. So, due to this, maintenance obviously can be decreases. Okay, synchronous motor has a high power factor correction, and they are used in areas where the power factor correction is needed. So synchronous motor have the high power factor correction. Wherever the high power factor correction is needed, then that process only we are going to use. Starting methods of the synchronous motor. So already we have studied in the machines all these things. Okay. What are the starting methods of the synchronous motor? Okay, as we all know that synchronous motor cannot self-start, so it has no starting torque. Therefore, we use to start the motor. External force is used to they start for bringing up the speed up to a synchronous speed. There are three main methods are there. There are three main methods to starting the synchronous motor. For reducing the frequency of the stator to a safe starting level. This is the one of the starting method of the synchronous motor. By using the external prime mover, this is the one of the method of starting the synchronous motor. And by use of damper winding, damper winding is nothing but it is placed in the poles. Okay, it is placed at the nearest the pole shoe. Clear? So this winding is can be placed to reduce the vibration of the motor. So this winding, damper winding, is used to use the what we can say, to reduce the vibrations of the motor. Clear? Applications areas of synchronous motor. Application areas of synchronous motor. The basic use of synchronous motor is power factor correction, which means to increase the power factor of system. Okay, synchronous motor are used in voltage regulation. Okay, synchronous motor are generally used in low speed, high power loads. Synchronous motors are used in voltage regulation. Okay, and synchronous motor are generally used for low speed, high power loads. Okay, wherever we require the low speed and high power is required, then that places we can use the synchronous motors. Synchronous motors are generally used in air and gas compressors and vacuum pumps and so on, etc. Synchronous motor also find their application in the crushers, mills, and grinders. Okay, synchronous motors can also be used in the crushers, mills, grinders, and so on, etc. They are also used in exhausters, fans, and blowers also. Advantage of the synchronous motors. The advantage of the synchronous motor is ability to control the power factor. So already we have discussed the power factor can be the power factor correction can be done by using synchronous motor. Okay, so this is the advantage of the synchronous motor. An over-excited synchronous motor has a leading power factor and is operated in parallel to the induction motor, thereby improving the system power factor. Speed remains constant irrespective of the loads. Okay, speed of the synchronous motor is remains constant. Okay, irrespective of the load. So this is quality helps in industrial machines where constant speed is required irrespective of the load. So means some industries require the constant speed, even though load, if the load is applied, the speed will be decreases. If the load decreases, the speed it will be increases. So but some industries require the constant speed irrespective of the load, whether it may be load increase or not, whether it may be load decrease or not, whatever it may be the load, but the speed should be constant. So in that places, okay, we can use a synchronous motor. Okay, for example, constant speed is nothing but for cutting the metals and for cutting the stones. Okay, we are using the machines for cutting the stones. Okay, there also we use the constant speed. Clear? Electromagnetic power varies nearly with the voltage in synchronous motors, and synchronous motors usually operate with a higher efficiencies more than the 90%, especially in low speed compared to the induction motor. So already we told the efficiency of the synchronous motor is somewhat higher than the induction motor. So what are the disadvantages are there? The disadvantage of the synchronous motors includes it requires DC excitation, which is supplied from the external sources. Means in the case of induction motor, we can say only we can give the only we need supply to give the stator. So no need to any external supply to the rotor circuit. That is one of the main advantage of the induction motor. But in the case of synchronous motor, we need one more extra supply, that is the DC supply for exciting the rotor circuit. Okay, that is the drawback of the synchronous motor. So these motors are not self-starting motors and need some external arrangement for its starting and synchronizing. Okay, as we know, three-phase induction motor is self-starting, but in the case of single-phase induction motor is not a self-starting. So we are going to use some capacitors to start the single-phase induction motor. Like the same way here also, the synchronous motor is also not having the sufficient starting torque. Due to this, okay, we have to arrange some external arrangement. We have to arrange some external arrangement for starting. This is the drawback. The cost per kilowatt output is commonly higher than that of induction motor. So the cost per kilowatt output, okay, is commonly higher than that of induction motor. So whatever we are getting the output mechanical power from the synchronous motor, okay, if we are calculating the per kilowatt, so this cost is very high than the induction motor or DC motors. So unless the incoming supply frequency is adjusted, there is no possible way to adjust the speed. So if you want to adjust the speed, okay, if you want to adjust the speed, so there is no other options to adjust the speed of the synchronous meter until and unless by adjusting the supply frequency. अगर supply frequency आपने adjust नहीं किया तो speed adjust करने का कोई chances ही नहीं इसमें. Okay, in anyhow we have to adjust the supply frequency. In anyhow we have to adjust the supply frequency. They cannot be started on load because its starting torque is 0. Okay, they cannot be started on load because its starting torque is 0. Okay, if starting condition में बहुत ज्यादा heavy load डाला है तो क्या हो जाएगा? The motor may be damaged because it is not having capable to produce the starting torque that much. Okay, the starting torque is almost all 0. So that's why this motor, synchronous motor, cannot be used where the high starting load is required. Clear? Collector rings and brushes are required, which results in the high maintenance cost. Synchronous motor cannot be useful for applications requiring frequent starting machines. Okay, this point should be modified. Okay, collector rings and brushes. Here also like a commutators. Here also commutators. We are using the collector rings. We are using the collector rings due to presence of these collector rings, and we are using the brushes also for we are using the brushes also in the synchronous motor for giving the DC supply to the rotor circuit, as well as we are using the collector rings. Okay, due to this, somewhat the maintenance is needed. Okay, if the maintenance needed means the cost of the maintenance is also going to increase. Okay, but it is somewhat less than the DC motors. Okay, because the commutator is present in the DC motors, but it is the commutator is not present in the synchronous motor. But brushes or collector rings are present. Synchronous motors cannot be useful for applications requiring frequent starting machines. Synchronous motors cannot be useful for applications requiring frequent starting machines. So means wherever we are starting the machine again and again, frequent starting. Okay, wherever if we want to start the machines again and again, okay, that places this synchronous motor is not perfect for that places. Okay, so these are the disadvantage of the synchronous motor. So he can see here equivalent circuit diagram of the already you have studied in the electrical machine subject. You have studied in the electrical machine subject equivalent circuit of the synchronous motor. Unlike the induction motor, the synchronous motor is connected to the two electrical systems: a DC source to the rotor terminals and AC system to the stator terminals. So unlike on induction motors, already we have told the induction motor is required only one supply, that is the AC supply, that is for stator only, stator winding only. But in the case of synchronous motor, it requires two DC supplies. Sorry, two supplies. One is the AC for stator, okay, that is the field winding. Another one is the DC for armature winding. Under normal operating conditions, synchronous motor operation, no voltage is induced in the rotor by the stator field because the rotor winding is rotating at the same speed as the stator field. Only the impressed direct current is present in the rotor winding, and ohmic resistance of the winding is the only opposition to it, as you can see in this figure. Okay, under normal operating synchronous motor operation, no voltage is induced in the rotor. No voltage is induced in the rotor by the stator field because the rotor winding is rotating at the same speed. The rotor winding is rotating at the same speed. So what is the meaning of this one? Because the case of induction motor, so always we have to compare with the induction motor. In the case of induction motor, we are giving the AC supply to the stator winding, and the EMF is induced in the rotor winding because the starting time the rotor is at standstill condition. Okay, we are not giving any supply to the rotor circuit. That's why there is no EMF is induced in the rotor circuit. Okay, so but when we are giving the supply to the stator winding, the EMF is induced across the rotor circuit also. But in the case of synchronous motor, under normal operating conditions also, okay, under normal operating conditions, no voltage is induced in the rotor by the stator field. because we are giving the two supplies. One is the stator, another one is the rotor. We are giving the two supplies. One is for the stator and another one is for the rotor circuits. So we are giving the both supplies. So how the EMF is induced in the rotor circuit? Clear? So that's why no EMF is induced in the rotor circuit because we are using the two supplies. In the stator winding, two effects are to be considered: the effect of stator field on the stator winding and the effect of the rotor field cutting winding. Rotor field cutting the stator conductor at the synchronous speed. So what we can say here, in the stator winding, two effects are to be considered. What are those two effects? One is the stator field on the stator winding, and another one the rotor field cutting the stator conductors at the synchronous speed. Clear? So in the stator winding, two effects to be considered. One is the stator field, okay, which is produced by the stator winding. Another one is the um, rotor field, which is produced by the DC supply, and this field is called the stator conductors at a synchronous speed. So this is the equivalent circuit diagram of the synchronous motor. Okay, this is the per phase. This is the per phase synchronous motors. एक एक phase का equivalent circuit diagram है, because this three phase synchronous motor, so three phases should be there. So each phase can be drawn the equivalent circuit in the form of equivalent circuit diagram. So you can take only one circuit, one phase. That phase is having the armature resistance, okay, and reactance and back EMF. The effect of stator field on the stator armature conductors is accounted by including an inductive reactance in the armature winding. This is called as synchronous reactance. Means what it is? The effect of rotor, the effect of stator field on the stator, okay, or armature conductors is accounted for by including the inductive reactance in the armature winding. So means what we can say here, the winding is having the property of inductive. So due to this nature of the inductance, it will have the reactance. It will have the reactance. Means the reactance is present. That reactance can be called as a stator reactance or synchronous reactance. That reactance can be called as a synchronous reactance. A resistance RA must be considered to be in series with the reactance. So always whenever we are having the winding, so that winding or that coil should have some amount of resistance. That winding or that coil should have some amount of resistance. Clear? So that resistance can be considered by a RA. That resistance can be considered by a RA. Okay. Next, this resistance combines with the synchronous reactance and gives the synchronous impedance of the machine. So means always we can say Z is equal to impedance R plus JXL, R plus JX. Okay, resistance plus reactance will give the impedance. So here also what we can say, the armature resistance, okay, the stator winding resistance and the synchronous reactance is combined with the impedance of the machine. Is combined with the impedance of the machine. Okay, the second effect is that voltage is generated in the stator winding by the synchronously revolving the field of the rotor. Okay, this generated EMF EB is known as back EMF. This generated EMF EB is known as back EMF and opposes the stator voltage. Okay, this voltage always opposes this voltage. Okay, so here you can observe you can write this KVL equation for this loop. Okay, if you neglect the voltage drop across this resistance and reactance, what we can say, minus V plus EB is equal to 0. So what we can write here, B is equal to V is equal to EB. V is equal to EB. So means this is the reverse polarities. Okay, so minus V minus EB is equal to 0. Polarities should be reverses. So minus V minus EB is equal to 0. Minus V is equal to EB. V is equal to minus V is equal to EB. So here back EMF is always opposes the terminal voltage, supplied voltage. Okay, the polarity should be changes here. Okay, so the magnitude of the EB is depends upon the rotor speed and rotor flux. The magnitude of the EB back EMF is depends upon the rotor speed and rotor flux per pole. Okay, since the rotor speed is constant, the value of EB depends upon the rotor flux per pole. That is exciting rotor current. That is exciting rotor current. Above circuit diagram means this is the equivalent circuit diagram of this synchronous motor per phase only. Okay, this schematic diagram for one phase of stator connected synchronous motor. Okay, and second one it will show the equivalent circuit referring to the equivalent circuit of 2.23. This is the equivalent circuit. This is the equivalent circuit. Just wait. Okay. So net voltage per phase in stator winding here is equal to E minus EB. This is the resultant voltage. Net voltage is nothing but result that is represented by ER. That is equal to V minus EB per phase. Okay. हाँ सर बोलो ना. Okay, the armature current per phase IA is equal to E is equal to resultant voltage upon by impedance. We know the formula I is equal to V by Z, or we can say V is equal to IZ. So by using these relations, here the V is nothing but resultant voltage that is represented by ER. IA is equal to ER upon by synchronous impedance that is represented by ZS. Okay, ER is nothing but resultant voltage. Okay, ZS is nothing but synchronous impedance. So by using this formula, we can easily find out the armature current. So here we know the formula ZS is equal to square root of RA square plus square root of RA square plus XS square. RA square plus armature resistance square plus synchronous reactance square. And also we can easily find out the ER. ER is equal to V minus EB. ER is equal to applied voltage minus back EMF, applied voltage minus back EMF. Clear? So you can draw the phasor diagram. So okay, already you have seen the machines to subject, I think. Okay, phasor diagram for lagging power factor, for unity power factor, for leading power factors. So no need to explain again here. So just take the brief idea. It will show the phasor diagrams for different field excitation. Different field excitation is nothing but over excitation and under excitation, like that. Okay, for different field excitation at constant load. One is represent the phasor diagram for normal excitation, EB is equal to V. Okay, phasor diagram for the normal excitation. When normal excitation condition is EB should be equal to the V. EB should be equal to the B. Okay, next, second one, phasor diagram for under excitation. Under excitation is nothing but back EMF less than the V, back EMF less than the V. Okay, so when the back EMF less than the supplied voltage, so means this is the under excitation. Under excitation, both cases the motor has lagging power factor. Okay, when the applied voltage is greater than the back EMF. Okay, in this case, the back EMF is not opposes the supplied voltage. In this case, the back EMF is not applied on the not opposes the supplied voltage. Okay, so means the magnitude of this back EMF is less than the magnitude of the applied voltage. Magnitude of the applied voltage. Clear? Next, so whenever this back applied voltage is greater than the back EMF, the motor will operate as a lagging power factor. So here, if we are taking the reference voltage V, so the in lagging power factor, the armature current is always lags with an angle of phi, okay, and EB is exactly 120 degrees to the leading to the 120 degrees lead to the supplied voltage. Clear? So this is the back EMF, this is the voltage. The resultant voltage will comes like this. The phasor sum of the the phasor sum of the EB plus V. Okay, so what we can say here, ER square is equal to phasor sum of EB square plus V square. It will give the resultant voltage. That is the resultant voltage that is represented by ER. Next, the phasor diagram when the field excitation is adjusted for a unity power factor. Okay, when the when the applied voltage, when the field excitation is adjusted for the unity power factor. So means unity power factor we are going to adjust the voltage. Okay, in this in such a way to get the unity power factor. Okay, we are going to adjust the field supply. Okay, we are going to adjust the field supply in order to get the unity power factor. So when we are getting the unity power factor, the voltage and current are always in phase. Okay, in phase means the phi is equal to 0 here. Phi is equal to 0. Okay, and the voltage and back EMF is same. Okay, this back EMF is leads the voltage with an angle of 120 degrees, and the resultant voltage ER is equal to phasor sum of the back EMF plus phasor sum of the this voltage. Next, leading power factor. When the leading power factor, when the EB opposes the supplied voltage. Okay, applied voltage is less than, okay, supplied voltage, excitation voltage is less than the back EMF. less than the back EMF, or back EMF is greater than the excitation voltage. When the back EMF is greater than the excitation voltage, then what will happening? The motor will operate at the leading power factor. Will operate in the leading power factor. In this case, the current is leads the voltage. The armature current is leads the excitation voltage with at an angle of phi. With at an angle of phi. So always how we can draw here? We can always see lagging and leading means I think you are all well known about the lagging and leading. For example, if you are taking the one parameter, for example, this is the x. If y parameter, okay, if y parameters lag the x with 90 degrees, lags means like this. For example, with some angle, this is the y. Okay, so the graph comes like this. It is lagging. So means the y parameter is lags x by with some angle. Some angle means that is represented by some degrees or whatever. Okay. If y is leads the x by some angle, so how we can draw? Take the x reference. Take the x reference, and y leads the x. Y leads means like this. We can draw here like this. So lead means in this direction. Okay, this y leads the x with some angle. With some angle. So here also leading power factor, the current leads the excitation voltage with some angle phi. And the back EMF and applied voltage is same as, and we are getting the resultant voltage like this. We are getting the resultant voltage like this. And but the angle between this resultant voltage and current will be changes. Okay, so if the armature current is leads the voltage, so our resultant voltage is also graph exactly 90 degrees to the now ER voltage, resultant voltage is exactly 90 degrees leads the excitation voltage. Resultant voltage leads exactly 90 degrees to the excitation voltage. Next, motor torque. So we can know the formula. Motor torque T is equal to 9.55 into Pm upon by Ns. Okay, here Pm is nothing but mechanical power. Okay, where Pm is the gross motor output in watts. Okay, where the gross motor output in watts. N is nothing but synchronous speed. And shaft torque TSH is equal to 9.55 into P shaft output. PSH out means shaft output power by NS. Okay, TSS is equal to shaft output torque T is equal to shaft power into 9.55 by NS. This is the gross torque and this is the shaft torque only. Gross torque is nothing but shaft torque plus losses. Shaft torque plus losses. Gross torque is equal to TSS is equal to so T gross plus losses. Okay, output of the mechanical power output of the shaft is equal to so total output power developed. Okay, total torque developed, that is called as gross torque plus losses. Losses क्यों बोलते हैं अपन? Because if any, this is the rotating part. Okay, some amount of energy is wasted in the form in terms of bearings and friction and so on, etc. That's why gross torque is equal to gross torque is equal to TSH minus losses. TSH minus losses. Okay, so means is equal to what we can see, input minus losses is equal to output. Input minus losses is equal to output. Like that way we can write. Okay, so you can see here from that relations we can write the equations. Mechanic PM is equal to V into EB upon by XS. Here voltage into back EMF. Voltage nothing but excitation voltage. Okay, excitation voltage into back EMF upon by reactance per phase. V into EB upon by XS for 3 phase. That is equal to 3 into. We have to write here 3 phase. 3 into EB upon by XS for 3 phase circuit. Okay, this is the per phase, and 3 phase click now the 3 into this. It is clear from above relation that mechanical power increases. With torque angle, electrical degrees, and its exact maximum value is reached when delta is equal to 90 degrees. So what we can say here? It is clear from the above relation the mechanical power increases. With torque angle. Okay, with torque angle in electrical degrees, and its maximum value is reached when the delta is equal to 90 degrees electrical. Okay, mechanical power कब improve होता है? When the mechanical power is increases with the torque angle in electrical degrees. Torque angle in electrical degrees, its maximum value is reached when the delta is equal to 90 degrees. Okay, when the delta is equal to 90 degrees, so obviously the mechanical power is also increases. The mechanical power is also increases because the mechanical power is directly proportional to the torque angle. The mechanical power is directly proportional to the torque angle. Okay. So we can discuss tomorrow. We can continue this lecture tomorrow. V curves and V inverted V curves and so on, etc. Only 21 students are present. What about the others? 9, 16, 9, 16, 1, 5, 11, 1, 5, 11, 13, 14, 18, 13, 14, 18, 13, 14, 18, 20, 21, 23, 20, 21, 23, 24, 26, 24, 26, 28, 39, 28, 39, 41, 41 के बाद 42, 47, 42, 47, 53, 55, 53, 55, 56, 57, 56, 57, 33, 19, 3, 19.